So far, we learned the principle of least squares and saw that the linear or the weighted linear least squares estimation is an appealing approach for solving overdetermined and inconsistent systems of observation equations. Until now, we have discussed the least squares estimation from the perspective of multivariate calculus, which was based on minimization of the S-squared norm of the residual vector. In this section, we want to discuss the very same concept of least squares, but from the perspective of linear algebra. This view gives an interesting and intuitive geometrical interpretation of the concepts of least squares. Please note that in this lecture, we use some mathematical concepts from linear algebra, for example, the concept of vector space, range space, and orthogonality. Familiarity with these concepts is very helpful for following this lecture. I suggest to already review these concepts in this section recap on linear algebra. We have learned so far that in the overdetermined and full rank system, that is when the number of observations is bigger than the number of unknowns, the system of equations is usually inconsistent and it does not have any exact solution. We also discussed the source of the inconsistency, that is mainly the presence of errors in the observations. In this kind of systems, the vector y does not lie in the column space or range space of matrix A. The range space of A is a space in which all vectors can be constructed as a linear combinations of the columns of A. Now assume we have the least squares estimation of x, denoted by x hat. Then the least squares solution for the observations can be also computed as y hat equals to ax hat. We can think of y hat as a vector of new adjusted observations for which the equation y hat equals ax has a solution, and the solution is given by x hat. In other words, y hat should lie in the range space of A. And so, because of the least squares principle, the distance between the original observation vector y and y hat should be minimum. That is, among all the vectors in the range space of A, y hat has a minimum distance to the vector y. Actually, the difference between observation vector y and its least squares estimate y hat is the vector of least squares residuals. Having the vector y hat in the range space of A with the minimum distance to the vector y implies that the vector of residuals should be normal or orthogonal to the range space of A. This means that all the vectors in the range space of A should be orthogonal to the E hat as well. For example, the first column of A is orthogonal to E hat. Also the second column. Actually, all the columns of the matrix A should be orthogonal to E hat. We know that the condition for orthogonality between two vectors is that their inner product must be equal to 0. So, we can then write this condition for all the columns of matrix A. For example, for the first column, it means that AC1 transpose multiplied to E hat is 0, and the same for the rest of the column vectors of A. If we group all the transpose columns in one matrix, the conditions can be written in this form. Note that this big matrix is a matrix that its rows are transpose of the columns of A. What I just said is the definition of matrix transpose. So we get A transpose E hat should equal 0. Let's insert y minus ax into this equation as E hat. Then we get A transpose y minus ax equals 0. And finally, A transpose y equals to A transpose ax hat. Do you remember this equation? This is actually the normal equation, which solution is given by x hat equals inverse of A transpose A multiplied by A transpose y. This is the least squares estimate of x. In fact, based on the orthogonality concept, we reached to the equation of least squares again. Also, the adjusted observation vector y hat can be also computed now by multiplying a to x hat. In fact, we can interpret the least squares estimate of y hat as the orthogonal projection of the original observation vector y on the range space of matrix A. And this projection can be written in the mathematical form as the multiplication of the matrix PA to the vector y. PA means orthogonal projection to the column space of A. Okay, so far so good. Now let's look at some exercises about the projection matrix and its properties, and then continue with a more intuitive example of this geometrical interpretation of least squares.